good exercise. We will go through a series of statements about basic Peron-Frobenius theory, and the sequence is also important. You cannot bypass that sequence, and it will contain many simple statements which require a short proof, and some of the more complicated statements I may not go over the proof completely, maybe just give you a reference. But all this is a very good exercise in mathematics, just logic, basic logic. In fact, linear algebra, the whole subject, proofs are very important and interesting. So that is the main thing. So you should not be casual. Even if the statement looks very easy, until and unless you are convinced that there is a proof that you have found. Proof may be one line, or proof may be half a sentence, but still, it is very important to sort of convince yourself that the proof is correct, and then only proceed. Because yesterday, while solving the problems, I got the feeling that you need to pick up the proof technique a little bit more. I mean, in your linear algebra course, some of these things may be done very fast. So now let us, so I'll do a series of statements, and I will go slow for even the simple proofs. And this is going to be basically another approach to Peron-Frobenius theorem, even the existence of positive eigenvalue and so on. So now look at this statement. I have a positive matrix. It has a positive eigenvalue, and there is a non-negative eigenvector. Then I want to show it is positive. Why? It is very easy, because suppose that eigenvector has a 0 somewhere. Suppose this is the eigenvector, and suppose somewhere it is a 0. Then because Ax is equal to lambda x, suppose this is the ith position. Then Ax ith position is 0, because Ax is equal to lambda x. But A is positive and x is non-negative. That implies Ax is strictly positive. Ax cannot have any 0 coordinate, because when you take Ax, it is just a linear combination of columns of A. Okay, that is the usual how matrix multiplication works. It's a linear combination of columns of A. x1 times the first column of A plus x2 times the second column of A, and dot, dot, dot. This viewpoint of matrix multiplication, one should always keep in mind. And so, because all the elements of A are positive, Ax is strictly positive. And so, this cannot happen. This cannot happen. So, this cannot happen. And so, X is positive. That is how we have proved this statement. So, many of the proofs are going to be of this type, that you have to be very careful about the steps. And later on, we will see that positivity of A is a very strong assumption. You don't need positivity. What you need is non-negativity and irreducibility. So I will introduce irreducibility, and then similar statement will be true for irreducible matrix also. Okay, so we now have the first statement that any positive matrix has a positive eigenvalue and a corresponding positive eigenvector. Okay, so now I want to proceed with further statement. And if we look at A transpose, then A transpose, we can apply the same method, and we conclude that A transpose has a positive eigenvalue and a corresponding positive eigenvector. Or you can say that A has a left eigenvalue. Last time I made a remark that you can think of left eigenvector also. In other words, if we apply the same method to A transpose, then we conclude that exists a y, vector y, such that A transpose. Now I'm going to use a different, not lambda, but mu. So I conclude that there is a positive number mu and a positive vector y, such that this equation holds. So at this moment we don't know whether lambda and mu are the same, but I claim that they are the same. Okay, but it is not obvious, because first I applied my theorem to A, then I got a positive eigenvalue and a positive eigenvector. Then the same thing I applied to A transpose. then I got a positive eigenvalue and a positive eigenvector. Of course, they need not be the same, but we will show that they are the same. Yeah, any question? Okay, so the basic idea here is to multiply on both sides. That means, so at present we have Ax is equal to lambda x and A transpose y is equal to mu y, where x and y are positive, lambda and mu are positive. So if I multiply this equation on the left by y transpose, and this trick will be often used. And now I know that y transpose A is equal to mu y transpose from the second equation. And so that is equal to lambda y transpose x. And x and y are positive, so y transpose x cannot be 0. And so we conclude that mu is equal to lambda. So actually, A transpose also has a positive eigenvalue. That is a trivial statement because A and A transpose have the same eigenvalues. But so if A has a positive eigenvalue, A transpose also has a positive eigenvalue. But to say that the same eigenvalue will have a positive eigenvector for A transpose, that requires a proof. And we have to use the whole Brouwer's fixed point theorem again by the same method. Okay, and that after doing that, we conclude that A transpose has a positive eigenvalue and a positive eigenvector. And now I have shown that they are in fact equal. Okay, so now I want to say that the next statement about this eigenvalue and eigenvector. So let us look at the concept of spectral radius. So if you have a general n by n matrix, a complex matrix even, and if these are the eigenvalues, these may be real or complex, and you look at their modulus. So if they are real numbers, that is just the absolute value, otherwise the modulus, and look at the maximum. That is called a spectral radius of it. Spectral radius. So it is just a number, it's a positive number, and by itself it may not be an eigenvalue. So geometrically what is happening is if you plot the eigenvalues as complex numbers in the complex plane, they may be lying everywhere apart from the usual condition that if lambda is there, then lambda bar is also there. And then this looks to be the one with the maximum modulus. So if I construct a circle with that radius, then the radius of this circle, that is the spectral radius. Now I claim that for a positive matrix, there is one eigenvalue we know it is positive. But all the other eigenvalues, they may be real or complex, but their modulus is less than or equal to that positive eigenvalue. So let me refer to this eigenvalue as the Peron eigenvalue or the Peron root of A. So that is the positive eigenvalue that we have got. At the moment, we don't know whether it is unique. That means there may be two eigenvalues with positive eigenvectors. How do you know that? There may be two positive eigenvalues with corresponding positive eigenvector, but in a moment we will see that that doesn't happen. There's a unique such positive eigenvalue. And let us refer to that as the Peron root of the matrix. And the next statement I want to prove is that any other eigenvalue. So let me take now Ax is equal to let me say that A nu is equal to lambda naught nu. So this is some equation where lambda naught is another eigenvalue. And I want to show, yeah.
When you said that we'll prove that there will be unique such eigenvalue,
yeah,
does it mean that the multiplicity of the eigenvalue will also be 1?
Yeah. Actually, I'll make what will happen later on is that that unique eigenvalue has algebraic multiplicity 1 also. And I was going to make a remark on that later, but let me say right now that because the algebraic multiplicity is 1, the geometric multiplicity also has to be 1, because
Right.
geometric is less than or equal to algebraic, and that is easier to prove. And that I will do. That will be my next statement after this statement. So the geometric multiplicity is 1, that's somewhat easy to prove. But then it is used. It is used to show that algebraic multiplicity is 1, and that proof I will not complete because that's a slightly longer proof, and I will give a reference where you can find that proof, but I will not give that proof completely. But it's a fact that algebraic multiplicity is also 1. Okay.
Excuse me, sir.
Yeah.
Yeah, you are referring to that Peron root as the eigenvalue that is corresponding to the spectral radius, or the one that is positive?
No. At the moment, we don't know that spectral radius is an eigenvalue. It's a fact, but it has to be proved. So Peron root I'm referring is the one eigenvalue which has a positive eigenvector. We showed that such exists.
Yeah.
That is the one I'm referring as the Peron root.
Okay.
But we will see that, in fact, this result I'm doing right now is going to show that that is in fact the spectral radius. So what I'm showing is, if you take any other eigenvalue lambda naught, and my aim is to show that modulus, remember lambda naught may be complex, and let me call that Peron eigenvalue as rho. I'll keep changing this notation somewhat. Sometimes I'll call it R for spectral radius, but you understand it from the context. So at the moment I mean this Peron root. This is the positive, this is positive eigenvalue with a positive eigenvector. Okay. Now one remark here. Here A is a positive matrix. Lambda naught may be real or even complex. And because of that, the vector nu will be real or complex. Okay, so we don't know anything about lambda naught and nu. Okay, so we will start with, I think I want to change the notation a little bit. And okay, so I think I'm going to change the notation a little bit. Please excuse this. I'm going to use a slightly different notation. Suppose AU is equal to mu u. Just the same equation I'm writing slightly differently. Okay, so here mu is a real or complex number. Mu is some other eigenvalue. Okay. Now if you look at summation Aij uj for any I, this is equal to mu ui by the eigenvalue eigenvector equation. And if you take the absolute, this is the modulus of that by the triangle inequality, this is less than or equal to summation over j. Mod Aij I don't have to put because Aij is positive. So I'll just write Aij mod uj. That is what I get. And on the left hand side, this is because AU is equal to mu u, this is nothing but mod mu ui from this equation, and that is equal to mod mu mod ui. So let me call this thing is a kind of a matrix. Let me refer to this as matrix A multiplied by u plus. What is the meaning of u plus? U plus is a vector where the entries are mod u1, mod u2, dot dot dot, and that is the notation. And if I rewrite this, then I get the equation AU plus is greater than or equal to mod mu u plus. I'm just rewriting this in a different way using a different notation. And now we will use the same trick. So left, right, pre-multiplying, right, left multiplying, right multiplying is a standard trick here. So I know that A has a left positive eigenvector or the eigenvector of A transpose. And I'll refer to that as Z. Sometimes I'll call this as the Peron vector actually. Peron vector means this is the positive vector eigenvector for A transpose. So if I left multiply by Z transpose, both sides, because Z transpose is positive, yeah.
Can you please define U plus again?
Yeah, U plus is a vector with elements mod U1, mod U2, dot, dot, dot. Okay, just the
Okay, fine.
absolutely. Okay. So now again here, this is a very subtle point that many times students, when they manipulate inequalities, they will multiply both sides and some keep the inequality. But you have to remember that when you multiply by something, unless you multiply by something positive, direction may be affected. But here that is not a problem because Z is positive. So I can multiply both sides by Z transpose and I get this inequality. Okay. But now if you look at the left hand side, Z transpose A is nothing but that eigenvalue whatever that eigenvalue lambda naught of that means the eigenvalue with the positive eigenvector. So in fact I can use the same rho here. So rho Z transpose U plus is greater than or equal to mod mu Z transpose U plus. And Z transpose and U plus, they are both positive. So I conclude from here that rho is greater than or equal to mod mu. So we have shown that any other eigenvalue, the modulus of that is less than or equal to rho. That means rho is in fact the spectral radius. So Peron root, we can also call it as a spectral radius. Is this clear? This proof? Very simple proof, but you have to watch the steps carefully. So let's go back to that picture of eigenvalues. So for a positive matrix, the picture looks like this now, that A is positive, then the eigenvalues in the complex plane, there's a certain disk, and this number, the real positive number, is the Peron eigenvalue, and that is also equal to the spectral radius of A. So many times the first statement of Peron's first statement, we can say that if A is a positive matrix, then the spectral radius of A is an eigenvalue of A. That is not in general true at all, because the earlier diagram I had, the one with the maximum modulus need not be an eigenvalue. But here it is true that the spectral radius of A is an eigenvalue of A. And all the other eigenvalues, now two questions. First of all, because this is the spectral radius, there is no eigenvalue outside this disk. That is the first statement. There is no eigenvalue outside the disk. All eigenvalues are inside. So one question is, can there be eigenvalues on the boundary? And this becomes a very interesting question, and there's a big combinatorial reasoning, which we will touch upon later, that there can be other eigenvalues, but not for a positive matrix. Okay, not for a positive matrix, for a non-negative matrix. There can be more eigenvalues. And how many are there? How are they located? All this we will see. Some of those statements are work of Frobenius, and I cannot complete. I'll give a reference. And also the eigenvalues inside are not random, not randomly located. They are located in a very structured way. And that also I'll tell you later. Okay, so now we have two statements. One is that A has a positive eigenvalue, a positive eigenvector, and that positive eigenvalue is the spectral radius. Okay, now I want to show that it has geometric multiplicity 1. So the rho has geometric multiplicity 1. So why is that? So now let me take the equation. So I think I'll fix the notation for the, I'm changing the notation a little bit, but so let me fix this notation for the, so this is the Peron eigenvalue. So or Peron root. So lambda naught is positive. A is strictly positive. This is my notation. So lambda naught is positive and y is positive. And now suppose, okay, just 1 minute. I used so suppose, I don't know what I should use for the Peron eigenvalue. So I don't want to, I think I'm using lambda naught. Okay, why I am using vector y, I am using for the Peron eigenvalue. And okay, let me just continue. So now suppose a nu is equal to nu. Yeah, sorry. Because I want to prove geometric multiplicity is 1, I think I should take the same lambda naught. Okay, so I'm all right with the notation. So suppose a nu is equal to lambda naught nu for some nu. That means there is another eigenvector. And to show that nu is a scalar multiple of y. That means geometric multiplicity is 1. Okay. Now here there is one remark that a is positive, lambda naught is positive, but still nu can be complex. There's no reason why nu has to be real, because if you take, but we can take the real part of nu. Actually, if here is one subtle point again, that if A is a positive, if A is a real matrix and if you have a real eigenvalue, this is a general statement, not about positive matrix. If A is a real matrix and it has a real eigenvalue, then the eigenvector can be assumed to be real, because if the eigenvector is not real, we can take its real part, that will also be an eigenvector. And we can take the imaginary part, and that will also be an eigenvector. I hope I'm making sense, because if A is a matrix, and because you can split it into the real part. So suppose A is positive, lambda naught is positive. If nu is complex, I'll split it into the real part and imaginary part and concentrate on the real part. That is a real vector. And I'll show that the real part is a scalar multiple of y. Then similarly, I will take the complex part and show that it is also a scalar multiple of y. So in other words, for the proof, we can assume without loss of generality that nu is real. Okay. Now here there is another technique which is very standard. If you look at these two equations, you look at y and subtract a multiple of nu. So let me use beta. Consider this, for where beta is some number, real number. This is also an eigenvector because it's a linear combination of y and nu. And when beta is 0, this is just y. So you start with 0, beta equal to 0, and suppose you increase it. Then this will remain non-negative, because when beta is 0, this vector is y, which is positive. So if you start increasing beta, for some time it will, by continuity, it will remain positive. But it will so happen that sometimes it will get a 0 coordinate. So you stop as soon as you get a 0 coordinate. So to summarize this, what I'm saying that there exists a number beta, a positive number beta, such that y minus beta nu is a non-negative vector with a 0, at least one 0 coordinate. I hope this statement is clear, because when beta is 0, it's a positive vector. You start increasing beta. This can be made more mathematical. Okay, you can find out the exact value of beta. Actually, it has to do with mod yi and mod nu I. I'm not doing that. It's very easy. but it is very easy to understand this way also, that when beta is 0, the vector is y, which is positive, and if you slowly increase beta, it will remain positive for some time, and sometime then it will get a 0 coordinate. So you stop as soon as you get a 0 coordinate, and that beta will satisfy this condition. Okay, so y minus beta nu is also an eigenvector, but it has a 0 coordinate. And now when a is positive, so I claim that in fact y minus beta nu, so that for that particular beta is actually equal to 0. Because if it is not equal to 0, then it's a non-negative eigenvector. And we saw that a non-negative eigenvector must be strictly positive. But it is not strictly positive because it has a 0 coordinate. So because of that, it has to be the 0 vector. And once it is a 0 vector, it shows that nu is a multiple of y. You can take 1 upon beta if you like. So nu is a scalar multiple of y. And now you can look at the real part of nu and the imaginary part of nu. Both of them will be eigenvectors and they will be scalar multiples. So this proof shows that the geometric multiplicity is equal to 1. I hope this is clear, because this part of Perron-Frobenius theory you will always at least remember. Proofs are not that technical. Okay, so I have shown that Perron eigenvalue has geometric multiplicity equal to 1. Okay, then I want to show one more statement, that if you take any eigenvector which is positive, take A and take, not necessarily for the Perron eigenvalue, but take the matrix A and take any eigenvector which is positive, then that must correspond to the Perron root. That's what I want to say. That means no other eigenvalue can have a positive eigenvector other than the Perron root. And this proof is quite simple. Again, this left and right multiplication. Okay, I hope the geometric multiplicity is clear.
Sir, how you claimed mu minus beta nu is equal to 0?
Okay, mu minus beta nu, we first of all saw it's an eigenvector.
Right.
Later on, we chose beta so that that vector is non-negative but has a 0 coordinate. Because I increase, right? Is it okay?
Yeah, you can choose beta so that one of the coordinate is 0.
And other coordinates are 0 or positive. Because when beta is 0, I have the vector y only.
Right.
Okay, and start increasing beta. When you start increasing beta, the vector will remain non-negative by continuity of the operation. It will remain non-negative, but at some point you will get 1 0 coordinate. That is the point. That is the point where I stop. And for that particular beta, we have a non-negative eigenvector with a 0 coordinate. Because
Yes,
okay, and such an eigenvector must be positive, we know. I proved in the very beginning today. If you have a non-negative eigenvector for a positive matrix, it has to be positive. Because it's a non-negative eigenvector, but the matrix is positive, so it has to be positive.
right.
And then but that's a contradiction because it has a 0 coordinate. So that's a contradiction. So that contradiction simply means that it must be the 0 vector, because if it's a 0 vector, it's not an eigenvector. And yeah, so that is how I concluded y minus beta nu is 0.
So here you are using what you proved very in the beginning.
Yeah.
If a non-negative vector is eigenvector for A and A is positive, then it has to have all the coordinate positive.
Yeah, I use that. Yeah, I very much use that.
Okay, thank you.
Okay, so now the next statement is that if you take, suppose A has, suppose AU is equal to mu u. So I have some other eigenvalue, but suppose u is positive. So I have some other eigenvalue with a positive eigenvector. I claim that mu must be in fact the spectral radius, the Peron eigenvalue. And for that, we just use that same pre and post pre-multiplication trick again. That means I pre-multiply by Z transpose, where Z is the Peron eigenvector for A transpose. So I get this equation. And as we did earlier, this Z transpose is rho times, rho times Z transpose U is equal to mu times Z transpose U. Again, Z transpose U is, because U is positive, Z is also positive, so this is non-zero. So rho is equal to mu. So this is a simple proof. What it says is, other than the Peron root, no other eigenvalue has a positive eigenvector. Okay, so this is just the basic Peron-Frobenius theory up to this point, which I think you can remember. I mean, you don't have to sort of, if you see it once and kind of present it once, then you will remember. Okay, so this is basic work of Peron essentially. And then we go to a non-negative matrix and try to generalize some of these things. And that is essentially where the work of Frobenius is coming in the picture. So I'll first talk about a directed graph associated with a matrix, with a non-negative matrix. So graph theory, again, I don't want to introduce graph theory, but perhaps you know what is a graph. It has a set of vertices and a set of edges. But we are just going to need the notation about directed graphs. So directed graph has some vertices. So this is a finite set. And there are directed edges. That means with an arrow. So there's an edge from this vertex to this vertex. And maybe this vertex to this vertex. And there can be, again, a edge backwards also. But we don't have two edges in the same direction. Actually, if we have two edges in the same direction, we can use a weight. We can put weight 2. So in one direction, there's only one edge, at most one edge. But this kind of a thing is all right. One edge this way, one edge backwards. And there can be loop also. That means an edge from a vertex to itself. That is okay. Let's go to loop. And so let us see a simple example. And I really don't need much graph theory at all. So just basic terminology and basic idea. And when we talk about the graph, it can be a real matrix, but we will always take a non-negative matrix, otherwise we don't need it. And in fact, for constructing the graph, it can be a 0-1 matrix also. But let me just have a non-negative matrix. So suppose you have a non-negative matrix. And what is the corresponding graph? So I need 3 vertices. They correspond to the rows or columns, 1, 2, 3. And so from 1, there is an arrow to 2. And I might put a weight of 2, but we don't really need the weights most of the time. We just need where the edges lie, because essentially we think of it as a pattern, 0-1 matrix. But if I need weights, I can put weight 2 on this to indicate that the entry is 2. But otherwise, I don't put any weight. Then from 1 to 3, also there's an edge, because the 1, 3 element is non-zero or positive. From 2 to 2, there is, because there's a loop, the diagonal element, this diagonal element is positive, so there's a loop. Then from 2 to 3, there is a directed edge. Finally, from 3 to 1 and 3 to 2. So that is the graph associated with this matrix. So we can make the usual definitions. What is a path? What is a, actually the path and walk, there's a small difference that in a walk, there can be repetition of vertices and edges, and path, there is no repetition. But again, for our purpose, if there's a walk, there's also a path because you can remove the repetitions. So for example, I have a path from 1 to 2. I have a path from any vertex to any vertex here essentially. So
Sir, one question.
yeah.
For example, this from this matrix you constructed this graph.
Yeah.
So even if say the entry A12 was 1, there
Yeah.
would be this in this just weightless, I mean unweighted
Yeah.
graph.
Yeah.
This will be the same graph, right?
Same
So
graph.
I'm asking that, is there any way where we can uniquely determine the graph by the matrix? I'm talking about only unweighted, not weighted. If we assign weight, then it will be okay. But if we talk about only take unweighted graph, can there be like just using properties of the matrix? Like for example, using the entries. So there are n square entries on the matrix A. So
Yeah.
using those entries only, is there any way to form different types of functions on the matrix so that we can maybe do this graph in a unique fashion? So corresponding to this matrix, only this graph can exist.
Yeah, but you will have to put somewhere the numbers, no? That means looking at the entries. Putting weights is one obvious thing, but somewhere you will have to bring the entries in the picture. Otherwise, how do you use that information?
Yes, that is.
So it can be done, but it is not going to be useful for our purpose right now. So putting weights is a very simple one. First way you can do it. If you put weights, then it becomes unique. That means from the graph, you can go back to the matrix if you know the weights.
Yes, from the graph going back to the matrix, there are several ways like adjacency, etc.
No. But that no. But adjacency is a 0-1 matrix only.
Yes.
So that is
course.
not, yeah. So you don't get the full matrix just by looking at the graph. You have to look at the weight somewhere.
Yes.
Sir,
Yeah.
if one allow
Yeah.
if one allow multi-graph, then it is possible, no?
No, multi-graph.
Because
No, but because how do you suppose the entry is pi? What do you do?
then we'll put 5 edges between.
No, not 5. No, not 5. I'm saying that the entry is pi. Then
Oh,
I mean just irrational
Okay.
number. Because even for rational numbers you may do something, but for irrational, so you definitely need to put actual weights. Multigraph won't solve the problem. If it's an integer kind of matrix, then multigraph will solve the problem, but otherwise no.
okay.
And also, yeah. So okay, the point here is even without using the numbers as weights, lot of information we are getting, and there's a lot of theory built around only this graph. That's what we will see. Very non-trivial theory. So given a non-negative matrix, just making it as a 0-1 matrix, that's what we are doing. Because we are just making every positive entry as a 1. And every 0, we are keeping it at 0. That's a, so if I change every element here to 1, I still get the same graph. And we are still getting a lot of information. And a lot of theory is built around that. But sometimes we will have to put the weights. Okay, let us look at how the matrix operations and this graph gets related. And the first very important example is what happens to the power or matrix multiplication. So if you look at A squared, suppose I know the graph of A. This is the graph of A, suppose. Can I construct the graph of A squared? So A is a non-negative matrix, keep that in mind. Can I construct the graph of A squared without even knowing the actual entries of A? I know only this graph. I don't know the weights, so I don't know the entries of A. But still it is possible to find the graph of A squared. Why? Because if you look at, so look at the elements A squared, ij. And all I need to know is whether this is positive or zero.
Sir, here we just have the information that we know graph of A.
Yeah, I'm hearing some other voices. I don't know. Yeah, what was the question?
Sir, I'm asking that here we just have the information that we know graph of A, and using that we are trying to construct graph of A square.
Right.
Okay. Okay. Thank you.
So if you look at the element Ij element of A squared, by matrix multiplication, this is nothing but summation Aik Akj. This is the matrix multiplication definition. And all I want to know is whether it is positive or zero, because it is definitely non-negative. And once I know whether it's positive or zero, I can construct a graph. For the graph, I just need to know which entries are positive and which are zero. Now, this will be positive provided if and only if Aik Akj is positive for some k. And that will happen if there is a k such that I to k there is an edge and k to j there is an edge. So if this happens in the graph of A, then this will be positive, which means that there is a path from I to j of length 2 edges. So that is how I know the pattern of A squared. So A squared Ij is positive if and only if there is a path from I to j in the graph of A of length 2. Of course, that requires a lot of counting and looking at the graph, but that's okay. I mean, I have not used any information about entries of A. So that's how you get the graph of A squared. So A squared, any element of A squared is positive if and only if there's a path. And the same thing applies to A cube. A cube also, A cube Ij will be positive if there is a path from I to j of length 3. Okay, so keep this in mind. So the powers of A are directly related to paths in the graph, existence of paths in the graph. This information we will use again and again. So that is how, given the graph of A, I know how to get the graph of A squared. Okay, now let's come to the connected notion, because in graph theory, in undirected usual graph, there are lots of connected. The graph is called connected. If, by the way, if you have in graph theory, if you have a simple graph which is not directed, just an undirected graph, you can always make it directed by replacing every edge by 2 edges, one in this direction, one in this direction. And then you can apply some of these terminology and many things will go through. But we will not do that. I mean, if necessary, you can do that. In particular, if you have a symmetric matrix, then essentially it becomes an undirected graph, because whenever there is an edge from I to j, there is also an edge from j to I. So it just becomes, I can erase the directions and it becomes an undirected graph. So directed graph we need for the broad picture, but you can relate it to undirected also. Now connectedness, so when do we say it is connected? In the usual case, we say it is connected if there's a path from any vertex to any other vertex. So here we will say that it is strongly connected. So first of all, I can also talk of connected here. I'll say it is connected if the corresponding undirected graph is connected. That means you erase the directions, make it undirected, and if that is connected, then this will be connected. But that definition will not be required that much. The more important definition that we need here is strongly connected. Strongly connected means there is a path from I to j for any I and j. For any I and j, there is a path from I to j, and this is a directed path. This is a directed path. For example, in this example, 1 to 1 to 3, there is one straight edge also, but there's a directed path 1 to 2, 2 to 3. And here I is not equal to j. So I am not demanding that diagonal loops should be there. No, that is not a requirement for strongly connected. Only so let me give some examples. So strongly connected means from every vertex to every other vertex, every distinct vertex, there should be a path, directed path. So if we take, like, suppose no loops are there, from 1 to 2 there is a path, from 3 to 2 there is a path, and 3 to 1 there is a path. Then this is essentially like becoming like a cycle, but this is not strongly connected because from 2 to 1, no path. There is no path. So this graph is not strongly connected. If you have one such pair for which there is no path from I to j, then this is not strongly connected.
Sir, is it connected graph?
The underlying undirected graph is connected.
But do we talk about the directed graph to be connected?
No, you can make one definition. As I said, I will make a definition that I will say that a directed graph is connected if the underlying undirected graph is connected. Okay.
Okay.
So according to that definition, this is connected.
Right.
But we will hardly ever need that definition. We will not need that definition. It's not going to be important in our theory. So you can keep that definition in mind, but it's not of much use. Or maybe it is used a little bit later on. But important definition is strongly connected. That is what we will repeatedly require. Connected, of course, this is connected. And if I add one more vertex, or say two more vertices here, and call it 4 and 5, then this whole graph is not connected because the underlying undirected graph is not connected. So there is no question. So clearly, if it is not connected, it is not strongly connected. If it is strongly connected, it will be connected. But connected definition, we will not require that much. Okay. And now I will make the definition of irreducible matrix. So take a non-negative matrix. So I'll give two definitions. One is this graph theoretic definition is called irreducible. If the associated graph, maybe I'll have a notation for this G of A or something, is strongly connected. Associated directed graph, of course, even if I don't say it, it's understood, is strongly connected. This is the only exception is this is for at least two by two, because if you have a 1 by 1 matrix, we always call it strongly connected because what is the, I mean, if you strictly go by the legal definition, 1 by 1 matrix, the corresponding graph. So suppose you have a 1 by 1 matrix. If that 1 by 1 matrix is non-zero or positive, then the corresponding graph will be a simple loop. But even if it is 0, the corresponding graph will be just a vertex. But a vertex is okay. I mean, this single vertex graph, it is strongly connected because there is no question of path from I to j. So using that strict definition also, 1 by 1 matrix is always strongly connected. This is just to keep in mind, not very important, but that is why 1 by 1 matrix is strongly connected, and 2 by 2 onwards, it is strongly connected if and only if the associated digraph is strongly connected. Now, can we can give the definition even without using graph theory, and what will that look like? And later on, we will see that the two are equivalent, or you can try to argue that they're equivalent. So for that, I take a non-negative matrix and I'll take a permutation matrix. So permutation matrix, if I pre-multiply and post-multiply by permutation matrix, I hope you know what is a permutation matrix. It's just the identity matrix with you permute the rows and columns, and that has the effect of permuting the rows and columns of A in the same fashion. And if after permuting, if it becomes like this, some B partition matrix, a zero matrix, some C and D, where B is R cross D, B and D are square. And suppose that is the picture. So B is R cross R. This is D. D is N minus R cross N minus R. If this happens, then we'll call A to be reducible, not irreducible, but reducible. And if this cannot be done for any permutation matrix, so it's a negative kind of way of defining irreducibility, we will say that A is irreducible if it is not reducible. Okay, so this is the matrix theoretic, purely matrix theoretic definition, that A is irreducible. Again, one vertex case is separate. So 2 by 2 onwards. A is irreducible if and only if, A is irreducible if it is not reducible. Now, why this definition and the earlier definition are equivalent? I'll just give a hint for that. You can make it more precise. See, when A is...
Sir, isn't it B, C, then 0D?
No. No. Okay, so those are equivalent actually. So there's one more exercise I'm giving you. So let's go back to... Yeah, I'll spend some time, just 2 minutes on this. If you take the graph of A, let me use this notation GA. So GA is the directed graph associated with A. And let's suppose I take A transpose. I claim that GA is strongly connected if and only if G of A transpose is strongly connected. Why is that? Because if I take the graph of A and if I reverse every edge, then I get the graph of A transpose. Okay, that's obvious. Because if there is an edge from I to J, I reverse it, I get every edge, I get the graph of A transpose. So if there's a path from I to J, there's a path from J to I also. And so if A is strong, if the graph of A is strongly connected, then the graph of A transpose is strongly connected, and conversely. And so I can also say that, that there's a permutation matrix Q such that Q transpose AQ is equal to B, C, 0, D, but they're equivalent. And again, interestingly, you might have seen this in some textbook. That's why perhaps you asked this question, and that's quite legitimate. It is not very easy to recognize that they are the same. You have to work. So that is why the graph theory is very useful sometimes, because with graph I can immediately understand, because graph of A and A transpose are essentially reversal of each other. So if one is strongly connected, the other is strongly connected. But here also this becomes an exercise. You have to spend some time at least to show that if A is reducible, all I'm saying is that if A is reducible, then A transpose is reducible. But you need to prove it, at least. Is this clear? At least 2-3 lines you will have to. Okay, so I hope this point is clear. So if you can do this, then you can also do this. That's an exercise, you can make it more precise. But if A is reducible, then A transpose is reducible. Okay, so now I will have again a series of statements about, so we want to extend this Peron's theorem to irreducible matrices. It turns out that the main insight of Frobenius was that positivity can be replaced by a weaker assumption of irreducibility. And still many of the statements that we had, they go through, almost all of them, barring a few statements about the number of eigenvalues on the boundary and so on. There you need some more structure. but otherwise they go through. Okay, so let's start with, I'll number these statements. So first statement is similar to our earlier statement, that if A is non-negative, so I'm not assuming positive, but I am assuming irreducible. So whatever we did with positive, now we are trying with irreducible. And if you have, suppose x is a non-negative vector, and suppose ax is 0. Then x is 0. For positive matrix, this is obvious. Because if x is non-negative and a is positive, then as we saw in that very first proof, that ax will be positive. So if ax is 0, x must be 0. But for irreducible also it is true, because very simple proof that just a one-line proof that suppose x is not 0 and suppose ith element is not 0, then ax is equal to 0 implies ith column of A is 0, because I made a remark earlier about how matrix multiplication works, because this is a linear combination of columns of A with coefficients x1, x2, and so on, and you will get xi times the ith column of A, and because xi is not 0 but ax is 0, the ith column of A is 0. But now a very simple observation, that irreducible matrix, an entire column cannot be 0. Because if an entire column is 0, suppose you have suppose the whole column, suppose some column is 0 entirely. That means nobody can access this vertex. So there is no question of strongly connected, because this vertex is kind of, there is no access from any vertex to this vertex. So this is, or similarly, if any row is 0, then from that vertex you cannot go anywhere. So it is not strongly connected. So entire column cannot be 0. So this is a contradiction, because A is irreducible. And so we have shown that x is 0. Okay, so just please see if this is clear. Okay, now one more property, interesting property of irreducible matrix, so I'll call it number 2, that, so again the same assumption, A non-negative, irreducible, and I'll assume that the order is at least 2 to avoid some trivial statements. And suppose I take a vector y, which is non-negative. Yeah.
Sir, in the earlier argument which you said that A is irreducible.
Yeah.
So we have assumed that if sum of the entry of A, that is column wise, it is 0.
Yeah. No, entire column.
Yeah, entire column is 0.
Yeah.
Then we can't talk about irreducible, because in the definition of irreducible, it should be like the matrix should not have any 0 entries. If it has a 0 entry, it implies that it is a reducible matrix.
No. Reducible, the 0 entries have to be a very structured way they have to come. What was the definition of reducible matrix? Reducible
Just a permutation matrix such that it
P transpose AP is that.
AP is upper triangular or lower triangular.
No, not upper triangular. These are block upper triangular.
Blocks upper triangle.
That means B, 0, C, D. But zeros can come definitely.
Okay. Yeah.
But all I said is that if you have irreducible matrix, entire column cannot be 0.
Yeah, okay.
And that is again immediate from the graph definition, because if entire column is 0, the graph cannot be strongly connected.
Yeah, got it.
Okay.
Thank you, sir.
Okay, so now, this is a very interesting property of irreducible matrix, that if you have an irreducible and y is non-negative, And suppose y has exactly k positive coordinates. Exactly k positive. So k is some number less than or equal to n coordinates. Then ax. So k I will assume is at least 1 and less. I'll assume it is less than or equal to n minus 1. Because if y is the whole vector is 0, then ay will, yeah, sorry, not ax, ay. Ay will be 0. Then ay, okay, not ay. I'll just take identity plus a times y has more than k positive coordinates. So it increases the number of positive, strictly increases the number of positive coordinates. So let me repeat. A is irreducible. Y is any non-negative vector. It has k positive coordinates. Then in plus a times y has more than k positive coordinate. Here, what is the effect of adding identity? When you add identity, you are just adding all the loops in the graph. That is the effect. So if you assume that A has positive diagonal entries, you don't need to add identity. Okay, so I think I'll just sketch the proof. I may not go very detailed, but this is the idea that you partition A.
Excuse me?
Yeah. Yes.
Excuse me, sir.
Yes. Yeah, what is the question? I think you are muted, I think. Is there a question?
Hi, sir. Hello.
Yeah.
Yeah. Can you please explain the statement, meaning of the statement, what the statement 2 is trying to say?
Yeah, when you take a vector matrix A which is irreducible and take a vector Y which is non-negative.
Yeah.
And if you go to this vector, in plus A times Y, then the number of positive coordinates in this vector is strictly more than the number of positive coordinates in Y. That's what I'm saying. So if Y has, for example, exactly 3 positive coordinates, then this will have more than 3, 4 or more. That is the same. Okay, I think I will not go to the proof, but I'll give a reference where, because I have to sort of at least give the basic statements. And proof is not very difficult, but it will take some time. You have to consider the partition matrix and so on. So I think I'll just proceed with the next statement, maybe return to this later on. I'll give a reference, that Ming's book I'll show you. And right now I'll just continue with the statements. As a consequence of this number 3 statement, we'll go to the next statement. That same assumptions as before, that non-negative irreducible n by n. This is an immediate consequence of the previous statement. Then if you take in plus a, actually this is to the power n minus 1. Then that is a strictly positive matrix. And in fact, the graph theoretic proof of this we have already seen. Because what is the graph theoretic proof? Because if A is irreducible, the corresponding graph is strongly connected. So if you look at any, for example, if you look at in plus a the ij element of this power, then from I to j, as long as I and j are distinct, there is a path of some length. But that path must have length at most n minus 1, because there are n vertices. If you go more than n minus 1, you will start getting a cycle. So that cycle you can ignore. So from I to j, there is a path, and I can take that path to be of length at most n minus 1. And so the interpretation we had for powers, that just says that the ij element of this matrix is positive. And this is true for any I and j except when I is equal to j. But when I is equal to j, because the identity matrix is there, that will take care of the I equal to j also. The identity matrix is there only to make sure that the diagonal elements in A are become positive. So that is the graph theoretic definition, or you can deduce it from the previous statement also, because if you look at, if you take any vector y, say non-negative but not 0, and if you look at I n plus a n minus 1 y, then every time you multiply by I n plus a, the number of positive coordinates increase. That is the previous result. And so after n minus 1 steps, it will become positive. So that is also purely matrix theoretic. Okay. So the next statement is that this is what we did for non-negative matrix, but now it is true for positive matrix, but now it is also true for irreducible matrix, that number 4, if you have, so if A is n by n irreducible, then any non-negative eigenvector is positive. So this statement we had, any non-negative eigenvector of A is positive. And suppose proof is very simple. If X is a non-negative eigenvector, then it is also an eigenvector of I plus A. And so take a non-negative vector of A. It is also an eigenvector of I plus A. It is also an eigenvector of I plus A power n minus 1, because they all A commutes with identity and so on. So it is also an eigenvector of any polynomial in A. And but this is irreducible. That was the previous result. So it is positive. Sorry, this is positive. That was the previous result. And we have shown that much earlier in the beginning today, that for a non-negative eigenvector of a positive matrix is positive. So this is positive. Okay, so I think I'll make some remarks here about the references and how you should proceed, because okay, I think I'll show you this Ming's book. It's a very nice book, because there are other books which are, they cover more material, like Berman and Plemons. Last time I mentioned 2-3 books, and Berman and Plemons was the classical book, but I think it has many other topics, so that may not be suitable. So this book is very good. It's a kind of at the undergraduate level, and so I'll just show you the contents. And it goes over, it covers, touches upon many topics in non-negative matrices. So the first property is about some linear transformation, and that's not what we are doing. Then localization. So I think basically what we are doing right now is this chapter 3. That means spectra of irreducible matrices. And so let me go to that chapter and Yeah, so yeah, this is what I did not say much about non-negative matrix. So it is showing the multiplicity of the eigenvalue of an irreducible matrix. But okay, basically I'm following some of these things that what we are doing. And okay, this is what I did right now. That if and only if there is a restatement of strongly connected. If and only if. Yeah, this is what I did just now. A non-negative eigenvector of a non-negative irreducible matrix must be strictly positive. So I want to continue with these results, but I will not be able to go into the proofs, I think, because that will take a lot of time. But it is my recommendation that after this series or whenever you get time, you should have a look at Ming's book, at least this chapter, and then follow the sequence of results. And that will essentially give you all the basics of Peron-Frobenius theory, whatever is required. And you can use it for basic applications. Only the first part is sufficient for it, but for slightly more applications, sometimes, especially Markov chains and so on, you need irreducibility. So you need, that is directly connected with Markov chain application. So Peron-Frobenius theory has many applications. One of them being application to Markov chains. And there all this theory is very, very important. So this basic Peron-Frobenius theory, I think you can pick up from this Ming's book. And it is recommended that you see Ming's book, because I have to then also talk about, of course, I'll continue with some more results, but the whole thing cannot be complete unless you look at these references. But this one reference is sufficient for the basic Peron-Frobenius theory. Okay, let me just show. So I'll not continue with these states. I'll return to that later on, maybe next time. So let me show you how the combinatorial ideas connected with Peron-Frobenius thing works. So suppose you take a non-negative matrix. So suppose you take a 3 by 3 matrix, and let us look at the characteristic. So if lambda is an eigenvalue, then, or let us take the non-negative matrix with the Peron eigenvalue. Peron eigenvalue is rho. So suppose rho is the Peron eigenvalue. So rho is also the spectral radius. Now, if you take a number which is bigger than rho, so suppose some number mu is bigger than rho. So if you take rho I minus a, that will be singular, of course, because rho is an eigenvalue. This is singular. But if you take mu I minus a, where mu is a number bigger than rho, then this matrix has many interesting properties. First of all, this is also non-singular. Why? This is not, I mean, rho I minus a is singular, but mu I minus a is non-singular. Why mu I minus a is non-singular? The very simple reason is mu is bigger than rho, and rho is a spectral radius. So mu cannot be an eigenvalue. Any number bigger than rho cannot be an eigenvalue. So mu is not an eigenvalue. So mu I minus a is singular, non-singular, and it has the entries have the property that all the off-diagonal entries, they are less than or equal to 0, because we are taking a non-negative matrix and then using minus A. So they are less than or equal to 0, all the off-diagonal entries. And diagonal entries, there is no restriction, but diagonal entries are in fact turn out to be positive. And so there are several simple statements about Peron eigenvalue. One simple statement is that just like you might have seen statement for a symmetric matrix, eigenvalue of a symmetric matrix. So similarly, the Peron eigenvalue dominates X transpose AX for any non-negative vector. So in particular, this requires a proof, of course, but in particular, rho is greater than or equal to any diagonal element. So because of that, mu is bigger than rho, so all the diagonal elements are positive, in fact. So such a matrix, that means a square matrix where the off diagonals are less than or equal to 0, and the matrix, the diagonal elements are positive, and it is, I mean, the mu is bigger than rho, then such a matrix is what is called an M matrix. So last time I was mentioning an M matrix, and it has many other definitions. So you can say that, so all the following conditions are equivalent. One can get a theorem like this, that so you have a matrix with off diagonals less than or equal to 0, and the following are equivalent. One is that, so you can use any definition of M matrix, but if you say all the principal minors are positive, there are several definitions coming from different areas. But what I want to do here is I want to look at this matrix, rho I minus A itself. So rho I minus A, that is sometimes called a singular M matrix. It is singular, definitely, because rho is an eigenvalue. That's called sometimes a singular M matrix. And what we know is that A has a non-negative eigenvector. I'm not assuming irreducibility or anything. So, but it is true that if A is a non-negative matrix only, so this statement is definitely true, that if A is just by continuity kind of argument, that if A is a non-negative matrix, no assumption about irreducibility or positivity, then it has a non-negative eigenvalue and it has a corresponding non-negative eigenvector. That much is true, and that can be done very easily by a continuity assumption, because if you like, you can add a small epsilon to all the elements. J is the matrix of all ones. This will become positive. This will have a positive eigenvalue and a positive eigenvector. And then you take the limit as epsilon go to 0, then definitely A will have a non-negative eigenvalue and a non-negative eigenvector. Of course, the non-negative means it can be, if A is the entire 0 matrix, then the eigenvalue is 0. But all I'm saying is it has a non-negative eigenvalue. Okay, so take A to be a non-negative matrix, and again the spectral radius is an eigenvalue. That will also be true. So suppose rho is the spectral radius, and or you can assume for the time being that A is irreducible, if you like, and look at the matrix rho I minus A. That's a singular M matrix. So I want to show combinatorially, give you some idea about the combinatorial way it works, that there is a non-negative eigenvector. That's what we already proved in Peron-Frobenius first statement, but I want to look at it differently. So look at the matrix rho I minus A more carefully. So rho minus A11 minus A12 minus A13. Let me write it out. Minus A21, rho minus A22, minus A23, minus A31, minus A32, rho minus A33. Then, as you know, if you take the adjoint matrix, that means if you look at the cofactor elements in this, so then any column of that, so as you know, A times the adjoint, if a matrix is singular, then this is 0. So apply that to this singular matrix. So the adjoint of this actually gives the coordinates in the eigenvector. So when you look at the cofactors, that means if you look at the determinant of, you delete one row and one column, and I just want to sort of go to a special case here that, so many times this is used in, sorry, I did not mention it earlier, that I also want to assume, because for applications, and that can be done essentially without loss of generality. So I'll explain why. I'll assume that A is stochastic. That means the row sum is equal to 1. All the row sums are equal to 1. And for all the Peron-Frobenius theory, actually, you can assume essentially without loss of generality that A is stochastic, because all you have to do is take a matrix A. Yeah, I'm going a bit too fast, but I think I want to show this combinatorial argument. So if you multiply each row by a constant, that doesn't change anything. So you can assume that every row sum is equal to 1 and then proceed. So stochasticity can be assumed. And when A is stochastic, that means the row sum, that means the summation of elements in any row is 1. And that means A times the vector 1, 1, 1 is equal to the vector 1, 1, 1. That is the meaning of stochastic matrix, the same definition. And that means 1 is the Peron eigenvalue, because here you can see that 1 is an eigenvalue and it has a positive eigenvector, namely the eigenvector of all ones. And so 1 is an eigenvalue. So for a stochastic matrix, 1 is the Peron eigenvalue. And
Hello, sir.
yeah.
So here, along with the assumption of stochastic matrix, you have also assumed that A is non-negative stochastic.
Yeah. Non-negativity is also there. Yes.
Yeah, okay, thank you.
Okay, so I want to rewrite this matrix where I want to put row equal to the row sum. Okay, so I think this will just take one more screen. So now I'm taking a stochastic matrix. Let's take a 3 by 3 matrix, stochastic matrix. So this is minus A12, this is minus A13, and this will be, because the spectral radius is 1. So when you subtract, this will become A12 plus A13, so that the row sum is 0. That is what will happen. And here it is minus, here it is minus 821. I think I just used 2-3 minutes more. So here you can use minus, you have minus 821, minus 831, minus 823, and here it will be 821 plus 823. Row sum is 0. Here it is minus 832, and here it is 831 plus 832. Okay, now if you look at the cofactors of this, because the cofactors of this are what is going to come in the eigenvector. Eigenvector means here the null vector, because I have already taken the spectral radius minus A. So I am interested in a null vector. I am interested in a vector such that x1, x2, x3, such that this is 0. And I want to show that it is non-negative, a non-negative eigenvector. And this is going to come from the cofactors. And a very interesting thing happens here combinatorial. So let's look at a determinant. Suppose I take this determinant.
Sir?
Yeah.
We have assumed that A is stochastic matrix.
Yeah.
So, sir, in the first entry, it should be 1 minus A12 minus A1.
No, but then I actually, this is not the A matrix. This is the row I minus A matrix. And here row is 1. Okay, so after doing that, this is the matrix, because then I'm looking at null vector, not the eigenvector.
Okay.
Because this is the row I minus A matrix.
Right.
Okay, so what I want to show you is works like magic. Why it is a magic? You look at any cofactor, any determinant of this, any cofactor. So suppose I take this cofactor, the 1, 2 rows and 2, 3 columns. then what is the determinant? So the determinant is A12, A23, the product, minus A13 multiplied by A21 plus A23. That is the determinant. And this is nothing but A12, A23 plus A13, A21 plus A13, A23. And as you can see, all the things here are positive. So this is positive. And this will work for, you can try it later on. It's really very surprising because even if you take this cofact, this determinant, you can work it out. There will be lots and lots of cancellations, and eventually you will get every single term will be positive in the expansion. And because every single term is positive, the eigenvector will be positive. So this is another proof that the null vector for the, so I am saying that this is that steady state vector for the Markov chain. So if you take the I minus, if A is a stochastic matrix, and if you take I minus A, then it has a positive null vector. And when you go to a large matrix, this becomes very, very surprising. At least when I saw it for the first time, I was quite surprised. That means suppose you take a very large, let's say 10 by 10 stochastic matrix, and then you go to the matrix I minus A, and it will be a big matrix. And you delete any row and any column. And so this is going to be any row and any column, but of course with the appropriate sign, because as you take in cofactor, it is -1 raised to the I plus j kind of thing. So delete that row. And this is a 9 by 9 matrix. You evaluate the determinant of that. It will be a very long expansion, but if you use a computer or something and do the complete expansion, you will get a sum of positive terms. All the negatives simply vanish. And that was very surprising. There are no negatives. There is a combinatorial reason for it. I'm not going into the combinatorial reason, but you can check this at least for a 3 by 3 or a 4 by 4 matrix. And so this is basically why combinate, and this has been used. This has been used in perturbation of Markov chains. That means when you perturb the matrix A, how does the eigenvector change? And here you have better control because all these. So this observation has applications also. Okay, so I think next time I'll complete this more results on non-negative, and then go to the concept of primitive, imprimitive, and so on. But I think you have to follow it up with some literature, Link's book or some other literature to sort of keep you up to that. Okay, I think I'll stop.
Thank you, sir, for this lecture.